classical networking, and why that leads to a completely different way in which you would think about network protocols compared to classical protocols that we're familiar with, like the ones we're using over the internet right now. So this work all started when I was collaborating with the group in China that put up this very famous experiment quite recently, or a few years ago now. This satellite that distributes entanglement, polarization entangled photons across about 1,500 kilometers distance across mainland China. And from that, they were able to do quantum key distribution and demonstrate secure quantum cryptography over quite a large distance using this satellite. And even though this is the very first proof of principle satellite, it got me really interested in thinking about, well, where's this all going to lead, and what's the future outlook for this? And that's what we'll be having a look at today. So starting from the beginning, I know that you've had introductory lectures already, but we'll revise some of the basic things anyway. So you all know what a qubit is. Some superposition of two logical basis states, 0 and 1, with complex amplitudes. And we're going to be interested in the question of how do we communicate qubits over very, very long distances, the way we do with normal bits in a classical network. So in addition to qubits like this, we're going to be interested in one type of resource called the Bell pair, which is a maximally entangled state, which I'm sure most of you have seen. So it's a superposition where you have two different parties, and they're either both 0 or both 1. But it's not like a classical mixture where it's probabilistically 0 or 1. They're in a joint superposition. And photonically, how do we go about actually representing a qubit? Well, there are many ways you can do that, but the two most common ways that you'll see in the literature are either polarization encoding, which is where you say a logical 0 state means that a single photon is horizontally polarized, or a single or the 1 state is when a single photon is vertically polarized. That's a very convenient way of doing it. Another way to do it is using dual rail encoding, which is what I've got on the figure on the right there. At the output there, you've got two optical modes, so two spatially separated optical modes, but you have one photon that's in a superposition between those two modes, and that makes your qubit. So you could associate the first rail with being a logical 0 and the second rail with being a logical 1. And this circuit that I've got drawn here shows how you can interconvert between polarization and dual rail encoding using a polarizing beam splitter. And a polarizing beam splitter is just a device, it's a mirror, but it's polarization dependent, so that the horizontal component gets completely reflected and the vertical component gets completely transmitted. And you can very easily see upon inspection that if you put a polarization encoded qubit through that, and then the horizontal bit gets, which is the logical 0, that then gets redirected out the top path, and the bottom path, which is the vertical, goes straight through, and that wave plate at the top rotates the polarization so that they both have the same polarization now. And that works in both directions. So we can use these interchangeably, these two ways of representing qubits using a single photon. So the biggest obstacle we have with communicating quantum information over long distances is associated with the no cloning theorem that those of you who have done elementary courses in quantum information will be familiar with this. It just says that if I give you an arbitrary single qubit state, it is not possible to make duplicates of it. In other words, this arbitrary state psi up here, there is no unitary process. In other words, no quantum operation that I can apply that takes one copy of that state plus some other ancillary register, which is initialized into some arbitrary value, and then leaves us with two copies of the original state. Okay, so the reason that we know that the no cloning theorem is true is by a proof by contradiction. I'll let you guys work this out if you want to, but you can easily show that if there exists a state phi that satisfies this property, and that if I choose a different state, psi, that satisfies this property, with a little bit of algebraic rearrangement, you could prove that that must imply that this holds, which means that the states are either orthogonal or identical. But that's what classical bits are. They're either orthogonal or identical, either 0 or 1. So this immediately tells us that we can clone classical information, but we can't clone arbitrary quantum information. But it's important to point out that this only applies if the states are unknown. If you know what the state is, obviously you can go and prepare as many copies of it as you want. But if you don't know what it is, then this is our big obstacle. Why is that such a big obstacle? Well, in the normal internet, if you think of how protocols like TCP/IP work, they ensure quality of service using effectively repeat until success strategies. If you have a packet of data and then it doesn't make it to its destination in a certain amount of time, it attempts it again. But that whole protocol works because you can make as many copies of the classical data as you want and have as many attempts as you want. This is immediately telling us we can't do that. And that's going to be a problem because qubits can be very, very valuable. They might be the output to a quantum computation, or something that's really hard to get the answer to. And you don't want to just lose it. So that's really the fundamental problem that we want to try and overcome. So how do we overcome that? Well, one way around it is using quantum state teleportation. So here I have my original qubit, and I also have one of these entangled states that I was talking about before. And in this picture, red lines represent quantum information, and time is going from left to right, and blue represents classical information. So I take 1/2 of the Bell pair and send it up this way, and do a joint measurement, a Bell measurement, so an entangling measurement that is, between the original qubit and 1/2 of the Bell pair. Then the other half of the Bell pair goes down this way, along with classical communication of what the measurement outcome was. There are 4 possible Bell states. So when I do this joint measurement, there are 4 possible outcomes I can get. I have to communicate that down to the other side. And then based on a correction, according to that classical information, I find that the quantum information is now down here, even though the original qubit never actually passed through a quantum channel to get from there to there. Or if you want to be a bit sneaky, you could say that actually there is a quantum channel, it's just that it goes back and forth in time. That's a perfectly legitimate thing to do in quantum mechanics because unitary operations are reversible. So for those of you who haven't seen the maths for this, this is how you can prove how quantum state teleportation works. We've got our qubit in call it system A. Then we've got a Bell pair between systems B and C. And then I'm going to come and do a Bell measurement by hitting it with this Bell projector from the left. Well, if you do that between A and B, then you find that what you're left with in C, for that particular Bell measurement here, this one that I've got drawn, is I get the same qubit at the output. But that's assuming that I got that particular measurement outcome. Suppose I got a different Bell measurement outcome. I got 0, 0, minus 1, 1. Well, if you worked through the mathematics from that, which you might be able to do in your head, then you'd see that you'd get alpha 0 minus beta 1 at the output. So that can easily be corrected by introducing a phase rotation, a Z operator on the qubit. So this is where the classical communication is necessary to correct the outcome at the end. So for each of the 4 possible Bell states, there'll always be a local correction that I can do that will recover the desired state down here. So how does that actually help us? Well, it helps us because our original qubit is an unknown quantum state. So we can't, the no cloning theorem tells us that we can't just keep reattempting sending it over and over again. But the Bell state, that's a known state. That's one that if we have a device that prepares Bell states, we can make as many copies as we want. So what are we going to do? Well, we'll focus on distributing Bell states between parties, and we can do that as many times as we want. And when it succeeds and the 2 parties have a Bell pair between them, Then we can complete the rest of the protocol using just classical information, which doesn't have any of these problems associated with no cloning. So quantum state teleportation is one of our nifty little tricks that lets us use entanglement to bypass the problem of the no cloning theorem. So from that, we can conclude that the quantum way to communicate qubits is not by sending qubits directly. What we do is we distribute entanglement, then we teleport the state. The state itself doesn't pass through any quantum channels. And the quality of the teleported state depends on the quality of the bell pair. So if there's noise in the bell pair, which is the thing that we're distributing, that will then get transferred onto the teleported state. But one of the things we're going to be looking at here is that if you have a whole bunch of bell pairs that are of bad quality, you can use various techniques to extend the range of them and to improve the quality of them that allows us to actually overcome some of the limitations of the quantum channels too. So in the optical context, suppose we're using our polarization encoded qubits here. How do we actually do these bell measurements, these things up here that are needed? And whoops. Yeah, so the joint measurement up here, that requires a bell measurement. So optically, I can do it using one of these polarizing beam splitters again. So here I've drawn out all 4 combinations of the inputs to a polarizing beam splitter, where each input has a polarization encoded qubit. So they can both be horizontal, they could both be vertical. One could be horizontal and one vertical, or the other way around. So if horizontal is always transmitted, then they pass straight through. And if vertical is always reflected, they both reflect off. And in the other instances, you get these combinations down here. So focusing on these top 2 cases, what you notice is that those 2 cases alone have 1 photon at each output. These ones here have 0 photons at one of the output and 2 photons at the other. So what that means is that if I measure an event where I measure 2 photons at one at each output, then I know that I either had HH or VV. Whereas if I get anything else, then it fails. So this actually gives us a way of doing what's called a partial bell measurement. It lets us project onto a bell state, but we can't distinguish all of them. We can only distinguish the ones where we get anti-bunching, in other words, 1 photon at each output, in which case we're left with this projector here. That is, we get projected onto what's called the even parity subspace, which is the same as a partial bell measurement. So that's one way that we can easily do it. You can do it deterministically as well, using a CNOT gate. You could go and build a CNOT gate, and a CNOT gate lets you distinguish all 4 bell states, but CNOT gates are also much more difficult to build optically, which is why I'm using this as an initial example. But in principle, you can do it deterministically too. So we've discussed quantum state teleportation as one of our ingredients. Another one that we're going to use is entanglement swapping. So imagine that we want to distribute entanglement over a very, very long distance. Imagine that Chinese satellite. Imagine that it wants to extend its range even further. Well, it's easy to see that with loss having exponential decay over distance as it goes through, fiber or free space, but through an atmosphere or whatever, you're almost never going to get bell pairs successfully arriving. So even then, our repeat until success strategy for distributing bell pairs could have exponentially low success probability if we've got a very long distance. So entanglement swapping lets us break it up into smaller segments that we can then combine together. The idea is if I have a bell pair here, so this one here is one of our 0, 0 plus 1, 1 states, and this is another one. If I take 1/2 of each of those bell pairs and do a joint measurement, a bell projection between those, what I'm left with is a bell pair between these outer 2 ones, keeping in mind that they were separated. They never actually came in contact with each other, those two qubits. But it's effectively like quantum state teleportation, except we're teleporting entanglement. So we can do this in a big cascade. You could have the same thing extending further and further down, and build up a very, very long range entanglement distribution mechanism by breaking it into smaller parts like that. So again, mathematically, for those of you interested, the way it works, down here we've got our two bell pairs between A, B, and C, D. Then we come in and do a bell measurement between the inner two, B and C, and you can easily see in your head, if you expand that out, you get a bell pair between A and D, which should never contacted with one another. So that's how we extend the length of a entanglement distribution. What about improving the quality? Because it's not just that as length increases, the loss rate is increasing, and that the chance of successfully getting bell pair distribution is decreasing exponentially, but also the quality is as well. Because as photons, if it's a polarization encoded photon going through the atmosphere example, there could be disturbances that rotate the polarization a little bit. That accumulates as well. So that leads us to another important ingredient in these networks, which is called entanglement purification, which lets us take two copies of a bell pair that are both a bit noisy and combine them together to create a single bell pair that has higher quality. So this here shows the input-output relationship for how this works. This represents the fidelity of the input state, the fidelity of the output state. The blue line just shows the break-even point, and the purple line shows what that input-output relationship is. So as long as the input fidelity of the bell pairs is greater than 1/2, then the output fidelity will be greater than what we started with. And that follows this formula down here at the bottom. And I'll explain how that comes about. So here I've drawn two different ways of doing entanglement purification. The top way, I've done it using CNOT gates. Here we've got bell pairs. They're traveling outwards here in this circuit. So down here and down here, they're our output bell pair. These CNOT gates do effectively parity projections, the way that we discussed. You could also do that here using the polarizing beam splitter, the same way that I discussed before, to do parity measurements. So let's imagine that that these qubits are going through a quantum channel which randomly flips the polarization or randomly rotates the polarization, flipping up H and B. This purification gives a way of reducing that error probability. So if I give you two copies of a bell pair, 0, 0 plus 1, 1, and suppose it's subject to a bit flip error, then that would convert into 0, 1 plus 1, 0. That's with a bit flip on one of the qubits. So now imagine how I had two copies of the state, and each of them with some probability P was getting transformed from the ideal bell state to the bit flipped version. What do these parity projections do? Well, if there were no errors, in other words, both of the bell pairs were the original expected state, then they would have matching parity. You would have two copies of 0, 0 plus 1, 1. And by looking at the parity of the matching qubits, they would have to match up. If, on the other hand, one of the bell pairs got a bit flip and ended up like that, now if you checked the parities of the matching qubits, you would find that they didn't match. So you could throw them away or correct it, depending upon what you're able to do. If, on the other hand, both of them had bit flips, then the parities would match again. And that's where this formula down here comes from. The denominator is telling us the probability that the device says, yes, the parities match. And that happens when either both of them flip or both of them don't flip, which is why we get the F squared or the 1 minus F squared. But the actual fidelity is is strictly the case where none of them got bit flips. So we get f squared in the numerator, which is the successful outcome, normalized by the probability of the device thinking it was successful, which is this denominator. And that's where that formula comes from. So this is also going to be very useful to us because it means that now if we have noisy channels and we just can mass produce Bell pairs, as many as we want, then we can start improving the quality of the Bell pairs to an extent that wouldn't be allowed by transmitting a single copy of the Bell pair. And that's another thing that we have an advantage with here, is that we can do this with Bell pairs. We can't do this directly with arbitrary qubits. So by combining this concept with the concept of quantum state teleportation, we not only have a way of overcoming the fact that qubits could be lost in our channel, but we can end up transmitting quantum information via teleportation with far higher quality than what is possible by single use of the channel. So combining those things all together, we get to the notion of quantum repeater networks. Here we had our entanglement swapping idea, our entanglement purification idea. And suppose we want to do a very long distance. So here, these little things here represent Bell pairs, of course. These represent multiple copies of them. And these segments represent length segments. So imagine we're dividing a really long distance link into shorter segments. What we initially do is we send all of these Bell pairs independently. Then pairwise, we purify them down into half as many. Then we do entanglement swapping, which joins these together, thereby extending those links. Then we purify them down again together, and so on. And you can do that as many times as you want, and in principle get to arbitrary distance lengths and arbitrarily good qualities. There is an obvious problem here, and that is that every time you do purification, you're cutting in half the number of Bell pairs that you have, which means that if you want really, really, really good quality, suppose you want to do n rounds of purification, that would require 2 to the power of n copies of Bell pairs to begin with. So there's a potential exponential overhead if you're not careful. So you still want really good channels. That reduces the number of Bell pairs you need given the exponential overhead. But this is in principle a way to get very, very long distances with very, very good quality. And what you'll immediately notice now is that everything we're talking about is all about Bell pairs. It's like our commodity in the future network. In the modern classical internet, our commodity is bandwidth, the ability to send arbitrary data packets like what I'm sending to you now. But in the quantum internet, it's not about arbitrary data packets. It's about entanglement, because that allows us to do everything else via teleportation and other sorts of protocols. And it also means that all of the infrastructure is standardized to producing exactly one type of thing, which is Bell pairs. But that leads to another interesting observation. Bell pairs are all identical. This whole concept of latency that we have in the normal classical internet, it has a very different interpretation here. If the Bell pair that I'm using to perform teleportation is always the same, it doesn't matter when I receive it. All that matters is the quality of it at the time that I want to use it, which led some colleagues, one of my colleagues, Sam and Devitt, to come up with this idea. Well, latency doesn't matter. People just need a big resource of Bell pairs and then complete their protocols using classical communication, which we already have. So why not just mass produce Bell pairs, put them in a boat and send them around the world like that? And that might sound like an absolutely stupid idea, but it's not. If any of you have ever done classical networking subjects, almost all of you will have heard the professor say at some point, you know, the highest bandwidth communications channel you can make, even by today's technology, is a truck full of DVDs. No cable in the world has that level of bandwidth as a truck full of DVDs. And that's true. But obviously we can't use that for doing a telephone call or something. That's why we don't do it. But here, latency isn't the issue. So there's nothing wrong with sending all of the entangled qubits in advance, because they're the same anyway. And then when we need them, we use them. Now, this is still a very long-term idea, because first of all, it means we need very, very long lifetime quantum memories, and they'd have to be error protected to make sure that they don't decay over time. But those are the same sorts of resources that future quantum computers will be needing anyway. So at the time when large-scale quantum computing becomes possible with error correction and fault tolerance, you could use the same technology to pack a whole bunch of bell pairs onto a boat and send one half one way and the other half the other way, and then those halves of bell pairs sit in warehouses waiting to be used. And the calculations were done on this, and it turns out that it's not a stupid idea. So what are we going to do with all this quantum information? We talked about teleportation. It seems mandatory to talk about quantum key distribution. So let's talk about how to do perfectly secure cryptography, quantum cryptography. So the first one of these was BB84, Burns and Brassard. And I'm sure most of you will have heard of this. And this is a quantum key distribution technique where you send single photons. So if I was trying to communicate with you, I would send you a whole bunch of single photons, whereby I send them randomly as either horizontal, vertical, diagonal, or anti-diagonal. So we'll call this 0, 1, plus, and minus. Those are the labels we use for those. And then the person I'm going to just randomly send those, where these ones here, horizontal and vertical, they correspond to 0 and 1 in the logical basis, and diagonal and anti-diagonal, they correspond to 0 and 1 in the diagonal basis. So in each type of encoding, in the horizontal, vertical, or diagonal, anti-diagonal, we can encode one bit of information. We're going to be randomly doing that, random bits and random bases. So randomly between all four of those possibilities. The person on the other side comes through and measures in those bases, either the horizontal, vertical basis or the diagonal, anti-diagonal basis. And when at the end of all of that, they classically communicate, and it doesn't have to be secure. And they just say, okay, Bob says, I measured in this basis, this basis, this basis, this basis. And Alice says, okay, well, on this instance, I sent in the same basis that you measured in. On this instance, I did 2, same on this instance. On these ones, we were mismatched. On those instances, you're going to get random measurements. In the ones where we matched, we're going to get consistent measurements. So at the end of all this, we just filter away the ones where we didn't match, and the sifted bits, they are ones where they are necessarily consistent. And after that, you're saying, well, where does the security come from now? Well, imagine there was someone in the middle trying to do an intercept resend attack. So Alice sent this one, and then an eavesdropper came in, and suppose that she doesn't know what to measure in either. Suppose she measured in that basis. Then she would get a random outcome. She would retransmit accordingly and retransmit randomized information, which means at the end, there would be some inconsistencies. So at the end, Alice and Bob just sacrifice some of their bits. And if there are inconsistencies, they know that there was an eavesdropper. So in other words, the quantum nature of measurement, the fact that whenever you do a measurement, you collapse the state, that ends up being statistically detectable at the end. And that statistical measure immediately identifies whether an eavesdropper took place. So this top part gives us a way of securely communicating random bits between Alice and Bob, where we can be absolutely certain that there was no one listening in between. That gives us a shared private key. You could use that in a normal private key crypto system like the ones we have at the moment. Or if you wanted absolutely perfect security, you do it using a one-time pad, which is where you take the exclusive OR of or modulo 2 addition of your message and your key to get your ciphertext. And then the decryption operation is identical. So it's a symmetric cipher. Now that is the only crypto system that exists that is perfectly secure, but it's extremely problematic in the sense that you need as many key bits as the length of your message, and you can't reuse the key. Because if you reuse the key, then you can start doing statistical attacks, because if you have two messages encrypted with the same key, then if you modulo those together, the key vanishes and you end up with something which only statistically dependent on the messages and very easy to break. So that's the BB84 protocol using single photons. We can also do it using entangled photons. It's exactly the same protocol, except that now instead of sending random bits, we share bell pairs in advance. And we note that if I've got a bell pair 0, 0 plus 1, 1, if you mathematically re-express that in the diagonal basis, it's exactly equivalent to plus, 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 minus, minus, or diagonal, diagonal, anti-diagonal, anti-diagonal. So whichever basis you choose to look in, the bell pair is the same. In other words, if the two sides measure in the same basis, they're guaranteed to get the same outcome. If they measure in different bases, they're guaranteed to get randomized outcomes. And after that, the rest of the same argument holds. So here's another immediate use for our entanglement distribution network. We share high quality entanglement, and then we can apply this to get perfectly secure one-time pad encryption. But all of that's very hard today, and at the moment, we don't really have the ability to distribute entanglement over very long distances. And the reason for that is that these quantum repeater networks that I've discussed, while it all sounded very simple in principle, using very, very simple equations, these are extraordinarily difficult things to build in real life. Because if you imagine that you've got bell pairs, photons coming in from different bell pairs, and then you want to do a bell measurement between them, they need to be perfectly aligned at that polarizing beam splitter to get perfect interference. Now, if I've got one photon coming from, Melbourne down that way, and the other photon coming from Brisbane, you can see that it's going to be very, very difficult to make them arrive, with microsecond precision for interference at a beam splitter. So it's not as simple as the equations make out. It's an extraordinarily difficult engineering problem, not to mention that our current bell pair sources are very low efficiency for the larger part. And so what this really means is, from an engineering perspective, we need things that we don't have yet. We need things like quantum memories, so that when one half of a bell pair comes from one provider, we can just hold it there in waiting while we wait for the other half, and then align them, and then do the entanglement swapping or the purification. All of that is stuff that we just don't have the technical capacity to do over on a large scale at the moment, and it's very difficult. So when you read about places like China, again, for example, I believe India has some on a smaller scale as well. Lots of places are beginning to build little metro area quantum key distribution networks. They're actually cheating. They're not doing proper quantum repeater networks with swapping and purification to create long-range entanglement. What they're actually doing is using a compromise called trusted nodes, which is where, if Alice wants to send a secret key to Bob, she has a perfectly secure link with another node nearby, and that node has a whole bunch of guys standing outside with guns and swords, making sure that nobody's coming in. And Alice has to trust that node to send the key on to the next trusted node, and then destroy the information so that no one can recover it, and trust them as well, make sure that nobody comes in with a gun. So this is actually what's being done at the moment when you read about these metro area networks. They're using trusted nodes which do measure and resend. So they're basically like known eavesdroppers, and they just have to be trusted to do the right thing. Nonetheless, this is a diagram of China's metro area quantum key distribution network for a number of cities: Beijing, Jinan, Shanghai, Haifa, and also a backbone connecting different cities. The orange line here with the yellow dots, those are all trusted nodes, and also their satellite. All of those dots, they're all trusted nodes. None of them are actually proper quantum repeaters. So you can see here that, oops, if suppose this guy up here, this blue guy here, wants to communicate with this guy down here for perfect security, he has to go through 1, 2, 3, 4 other nodes to get there. If any single one of them is not trusted, in other words, okay, so this is in China, suppose the CIA comes in and compromises any one of these nodes in between, then that whole chain is compromised and it has no security at all. The CIA knows everything. So for the full length of the path, every single node, if any one of them is compromised, the entire path is compromised. So we very quickly see that this is fine for a small scale because there's a small number of these trusted nodes and you can just heavily fortify them and make sure that they're very, very secure. But if you really wanted to work to a large scale global network like this, there are too many things that you have to trust. And it's just not going to give us the expected level of security that quantum key distribution promises, because in principle, it can promise perfect security, which this isn't. So we're stuck in this situation where we have to accept some compromises to our security because the technology doesn't exist for long-range perfect security yet. But there are still some other classical techniques that we can use to improve this, to get something slightly better than what I said in between. Let's have a look at that. And this is using multipath networking for quantum key distribution. So the first thing I want to note, suppose I give you a bunch of keys. These are all random bit strings. And then I do the exclusive OR to all of them together, as many as you want. A property of that is that it is not possible to know the final key unless you know all of the keys that are being exclusive ORed together. If there's a single one that you don't know, in other words, if an eavesdropper comes in and gets all of the keys, then she knows what the final key is. But if she doesn't know just a single one of them, then she can't know what that final key is. So we're going to exploit this now. So for a single path, if we call P the P node, the probability that a node is secure, and we're going to have to go through a path of these like this of some length, and I'll call L the length, the number of nodes between the endpoints. Then for that path is secure if all L of those trusted nodes are secure. What if I use multiple paths? Whoops. What if I used multiple paths? So instead of one, I used a bunch like this. This is Alice, this is Bob, and I can choose a path like here and a path like here to get key 1 and key 2, which go into this idea to give us a net key that is k equals k1 mod k2. Now we have a situation where both of those paths have to be compromised for the final key to be compromised. So we can very quickly establish this condition for multipath, that if I is going over all of the different paths, then that's the probability that the full thing is secure. And we immediately have the mathematical observation here that this final result for the multipath security is strictly better than using any single path. So coming back to China's network here as an example, let's try and apply this in principle to looking at the topology of this network. Well, going down the backbone here, it's clear that there's only ever one path that's possible. There isn't any choice about it. So along the backbone, there are always going to be single points of failure. What about considering trying to communicate from here to here? Well, now we can immediately see that it's sitting on this cyclic path. We could get one key going this way, key 1, and another key going this way, key 2, and then we have that the final key is key 1 mod key 2, and it would require the CIA to come in and compromise both of these paths in order to compromise the security from this point here to this point here. If we look at some of these other topologies, some of them are not so obvious, but like this one here, you can see that there are cycles in here again. So if this person wanted to communicate with this person, they could get a key going that way and a key going that way. But all of these topologies on the screen, none of them have any more, as far as I can tell, anything more than twofold redundancy. So you can get this quadratic improvement in the effective trusted node probability. But the long-term goal would be to replace all of this with proper quantum repeater networks, which is technology that we just don't have. So what else can we do apart from quantum key distribution? By the way, everybody talks about quantum key distribution as though that's what it's all about. No, we're never going to be rolling out all of this technology for the purposes of quantum key distribution, because it's almost certain that the post-quantum cryptography will be standardized in the coming years, and then it makes it a whole lot cheaper and a whole lot easier. So everybody uses quantum key distribution because it's the easiest thing to explain, and everybody demonstrates it because it's the only thing that our engineers are smart enough to do. Nobody knows how to build quantum computers yet. So everybody talks about QKD because it's all they can do. Let's talk about other things that they can do. Using GHZ states, you can do quantum anonymous broadcasting. So what's quantum anonymous broadcasting? Imagine you've got the United Nations Security Council. Everybody's sitting there. They need to vote on something, or people want the opportunity to speak within the meeting, but they want to do it anonymously, so that if someone speaks, everybody can hear it, but nobody knows who said it. So we can do that using GHZ states, which are like a generalization of Bell pairs. Whoops. And you can make them from multiple Bell pairs as well. So here I've got a 3-party GHZ state. You can implement that protocol, quantum anonymous broadcasting, using distributed GHZ states. The way you do it is, let's assume that at most one person wants to speak. If that person wants to say nothing, they do nothing. If they want to communicate the bit 1, then they apply a Z gate to their qubit, which puts a minus sign in between in the GHZ state there. But that minus sign isn't associated with any single party. It's just a phase factor, which is common to all of them. And so at the end, they go through and all measure out in the diagonal basis, and they collectively determine what the phase is. The phase encodes the bit of information that's been communicated. And so that can be done using Bell pairs as a starting point and Bell measurements to build them up. Another thing that's being looked at for long-range entanglement distribution is quantum telescopy, whereby at the moment we have these big telescope arrays, which give you an effectively larger aperture for doing telescopic measurements. With entanglement, rather than just classical communication, it turns out that you can significantly improve the resolution of those types of distributed antenna arrays or telescope arrays. And there are lots of other things: anonymous voting, clock synchronization, all manner of cryptographic protocols. They don't really interest me either, any of these things. What I'm really interested in is quantum computing, because that's where the money is, okay? So we all know that the real reason we're interested in quantum technology is not because of quantum key distribution, it's because of quantum computing. End of story. So how does all of this affect quantum computing? At the moment, in the classical internet, we rely on cloud architecture, we rely on supercomputers. You can access a supercomputer from your phone if you want to. If you've got login permission, you can log into a massive supercomputer from your phone. We would like to see this sort of functionality develop in the future quantum era with quantum computers as well. But there are some big differences there. The reason we use cloud quantum computing at the moment is really just because it makes it more efficient if high intensity calculations are done in a centralized way, and huge amounts of storage are not held on small devices, but in a centralized way. It's primarily cost and computational efficiency, but there's no actual real computational gain. If I take 10 classical computers and network them together, the whole networked computer still has the same power as 10 classical computers. So you don't get any direct real enhancement from it. That's not the case with quantum computers, because quantum computers, as we know, the power of them scales potentially exponentially with the number of qubits or quantum cores or whatever you want to call it inside the device. In other words, if I take two quantum computers and unify them to collectively act as one, I don't just get something that's the sum of the parts like you do with classical computers. You end up with something way, way more powerful. So yeah, here's basically what you do classically. You have a root node, you distribute some algorithms around, but at the end of it, you just get a k-fold increase if you've got k computers involved. Quantum computers, not the case. If our quantum computer has computational power that scales exponentially with the number of qubits in it, then if they're networked properly together to act as a unified quantum computer, it's not acting as n1 plus n2 plus n3 and so on. It's acting with that amount in the exponent. So we get huge leverage by unifying remote quantum computers compared to doing it classically. So there's even bigger incentive to unify quantum computers in the future quantum era than there is today in the classical era. And we already know that today in the classical era, most of our devices would not have much use if it weren't for the networking capabilities. That's going to be an even stronger argument in the future. So to look at how this works, we're going to talk about this measurement-based model for quantum computing. I think most of you will be familiar with the normal circuit-based model where you have lines representing qubits and you have gates acting on them, and time goes from left to right. That's a very logical way of thinking about quantum circuits. A completely equivalent way of thinking about it is this measurement-based model, where we start with qubits. That's what the vertices here are. They're all initialized into the plus state, which is a superposition of 0 and 1. And the edges represent the application of controlled phase gates, which are entangling gates. So you can sort of visualize this as qubits where the links between them represent nearest neighbor entanglement. It turns out that if you can build a lattice of sufficient size like this, you can implement any arbitrary quantum computation on it by just measuring out the qubits, doing single qubit measurements on this massive entangled state. Okay, so the measurement-based model transforms the way we think about quantum computation. It's not about starting with the state and then performing operations on it to get the output. In the measurement-based model, it's you prepare a particular state that has a particular topology, and then you measure out qubits in a certain order and in a certain basis, and then the final leftover ones give you the output to your computation. Those two models are isomorphic, they map to one another, but this one is more convenient for explaining how distributed quantum computing works. And it works like this. Suppose node 1 has a little lattice cluster state like this. And node 2 has another little lattice cluster state like this. By distributing bell pairs between them using our quantum internet that we just discussed, they act as links, as long distance links between those two lattices. So now I can take two long range lattices that are individually prepared, one in Africa, one in China, one in the United States, and then with long range entanglement links, they get fused together into a big distributed graph state like that, a big distributed quantum computer effectively, which allows a much larger quantum computation to be implemented than what any of the individual ones could do on their own, and has exponentially more power than what any of them on their own could all do added up. Which leads to what some insights into what the incentives are for how we might build quantum computers in the future. And that is that building them in a highly modularized way, like I've drawn up here, the quantum Lego idea, that would seem like a logical way to do it. You have devices which can produce small graph states, you know, or by small, I mean, they could still be large, but some finite size graph state. They have optical interconnects that allow these entanglement links to be made to other lattices. And then these are all collectively entangled via these links, giving us a big virtual cluster state that's, that has far more power than the sum of the parts operating independently. And that's where the quantum internet can come into this, because the bell pairs are what enable those links to be made over long distances. In fact, a bell pair is exactly the same as a 2-qubit graph state. They're the same up to local operations. So effectively, entanglement distribution is distributing very, very small graph states. Okay, so now we're getting an idea of how the whole model might start looking in the future. Obviously, this infrastructure is going to be incredibly expensive. You're not going to realistically have a quantum computer at home in the same way that we outsource all of our computations these days off to, you know, Amazon Web Services or whatever, because it's more efficient to do it. We'll be doing the same thing in the future, but all of those individual data centers, if they were all linked by entanglement links, they could be super powerful acting together. But that raises the other question. We know that security is also important. If I'm going to outsource computations this way, and keeping in mind that if all of these global quantum computers are unified together, there could be all sorts of untrusted parties involved. You know, it could be on any country on Earth. It could be susceptible to being disrupted or intercepted by anyone. In a big unified environment like that, you need to trust the people that are executing your computations, especially given that the sorts of computations that quantum computers are going to be doing are going to be really, really valuable ones. Things related to drug design or materials design, optimization, supply chains, whatever, things that have a lot of economic value. That's why we're pursuing them. So we want this client to be able to interface with the cloud, but you know, with an encrypted shield around them, so that they can execute their data without the cloud environment knowing what the data is. At the moment, we don't do that. It's a technique called homomorphic encryption. The idea that data can be processed in encrypted form without the person doing the computation decrypting it first. Now, classically, this is not a practical thing to do, which is why we don't do it. We just trust AWS or Apple or Microsoft not to steal all our information, and it's a pretty bad assumption, as we all know. But with the quantum computing, we can actually solve that problem. We can do homomorphic encryption very, very well. So here's there are actually multiple various ways of doing it. One definition is blind quantum computing, and the other one's homomorphic encryption. This is homomorphic encryption. There's a subset of quantum operations called the Clifford operations, and they have the property that they commute with the Pauli operators. The Pauli operators X, Y, Z, and I. So these are single qubit operators. The Clifford group is the set of all computations that commute with these operators. In other words, if I put some set of Pauli operators before a Clifford computation, it's the equivalent as some potentially different set of Pauli operators after the computation, but with the same computation. Okay, so how can we utilize that for securely outsourcing computations? Well, if these are all my logical qubits, this is all on Alice's side here, the client. She's going to randomly choose Pauli operators to apply to all of her qubits. She knows what they are, and they act as her secret key. This is the server. That's Bob. He does the computation and sends it back to Alice, and she's able to undo it because there's another associated set of Pauli operations. So Alice is able to scramble the data using random Pauli operations, unscramble it at the end, And unless the server in between knows what those scrambling operations are, it turns out he can get zero information about what the data was. And the reason for that is that randomly applying Pauli operators with equal probability to each qubit is the equivalent of applying a perfect depolarizing channel. So perfect depolarizing channel is if for some state rho, with equal probability, I apply either I, X, Y, or Z, all with 1/4 probability. If I do that, I always get the maximally mixed state, independent of the input state. So from Bob's perspective, he sees a maximally mixed state that has no information about the input state at all, because he doesn't know what the Pauli operators were. Alice, she does, and she recovers the computation. So now we have a really, really cool model for how to go about doing this whole cloud quantum computing thing in the future. We can unify all the world's quantum computers using a big entanglement distribution network. All of the world's resources can be combined into something far more powerful than the sum of the parts, which is not what we get at the moment. We get something far less than that. And it doesn't matter if they're not trustworthy, because we can scramble all the information, get it all back, and be absolutely certain that nobody knows a thing about it, even if it was our worst enemy that was intercepting the data. Okay, so that's my big motivating force for why I think all of this is interesting. Now I want to go back to entanglement distribution networks, now that you know my motivation. This is a technique called quantum cost vector analysis for how we can actually go about analyzing how these networks for entanglement distribution perform. Now, in the classical internet, algorithms like TCP/IP, the internet is hugely interconnected. There are connections everywhere. How does it decide how to get a data packet from one point to another? Well, one way to do it is using shortest path algorithms, like down here. We say, what's the distance or the cost of using a link? We find the shortest one, and then we send our data packet from A to B that way. Okay, that's a perfectly sensible thing to do if you're sending classical data, and these algorithms are efficient. Dijkstra's algorithm solves the shortest path algorithm efficiently, no exponential overhead or anything. Suppose we want to do the same thing with our quantum entanglement. Well, what are the sorts of things we're interested in? We're interested in things like, what's the chance of the qubit being lost? What's the chance of it gathering noise, for example, a depolarizing or a dephasing channel or whatever? Those can be converted. So these are written in the quantum process formalism, for those of you who are familiar with it, so for loss, I say, with some probability P, I get my original state, and with some probability 1 minus P, I get the vacuum state. Or the depolarizing channel, with some probability P, I get my original state. Otherwise, I get the completely noisy, the completely mixed state. If you apply multiple such channels in succession, you can see that the total probability multiplies. But if we convert that into log form, then it becomes additive. So what we can do is take things like loss channels, depolarizing channels, bit flip channels, convert them into this logarithmic metric form, and then they become compatible with things like shortest path algorithms. But in quantum information, as we know, with entanglement, sometimes it's best not to use just one path. We know that we can do purification, so why not use multiple paths? Instead of using just the best one available, use the best one and the second best available paths both together, and then purify them at the end. And so long as both of these have fidelities greater than a half, we know that the final thing is going to be better than either of those two individual paths. So so for comparison, this is what we do in classical networks. We just find the best available way of getting from one place to the next. In the quantum case, we can take as many as we want. If we're talking about entanglement distribution, purify it all together and get something way better than what we started with. And this leads to various graph identities. So purification is where we have things in parallel collapsing down. So if we identify in our network topology these types of substructures, we can collapse them down So multi-cycles like this get converted down into higher fidelity links. Linear chains like this, if those are entanglement swapping operations, they get converted to a single longer range link. And so unlike classical information, where it's all about, in whatever our complex network is, we want to find the shortest path to get from one place to the next. Now our goal is to find the optimal area in the graph to use and then purify it all down for our purposes. We've got a different way of thinking about it. It's not just shortest path, it's multi-path. And the goal is to find the optimal set of multiple paths, or the optimal area or region of the graph, optimal subgraph, to purify down to create the best possible entanglement between two sources. So in a multi-user network, you can think of it like this. In a multi-user classical network, you would think about multi-user shortest path algorithms. We're going to instead be thinking about graph partitioning, whereby we partition for every user pair, A1, B1, that wants a link. We partition the graph around them and figure out what the best way to do that is, to subdivide it up so that it can all be purified down to give every user pair the best possible outcome. And we implemented a software package to do this. This is freely available on GitHub. It was created by my PhD student Hudson Leone and several other students, called QNet. And it implements all these things, free to download. You're welcome to give it a go if you like. And these are the sorts of things it does. This is an output from it, where that graph on the right, we've got a lattice graph, and we've got 3 different user pairs represented by different colors. And we've asked this greedy shortest path algorithm, which effectively goes through and takes multiple available shortest paths and then purifies them. This is the output it gave us for that graph, telling us for the green user pair to get the best pair from there to there, they should be taking that path and that path. And similarly for the orange ones, where we've specified that at most they can each use 2 paths. So all of this is now algorithmically implemented, and we can start actually modeling what large-scale networks look like using these concepts of swapping and purification and multi-path reduction. We can also model memory in these networks. You can imagine that, well, certainly one of the biggest problems that we have in the classical internet, the reason we need algorithms like, or protocols like TCP/IP, is for the larger part because of network congestion. If everybody's using the network at the same time, packets can collide and they have to compete and they have to be held until the network is available. We can model congestion avoidance graph theoretically as well, using this notion of temporal metagraphs. The idea is that if each of this layer represents our actual network, the multiple layers represent different steps in time, t equals 1, t equals 2, and so on. And then vertical links, they represent quantum memories. So if I've got a qubit starting here and it stays in quantum memory, then that's going down to the next layer. But if it doesn't go in quantum memory, then it would just traverse normally spatially. So by building up a graph like this, we can model quantum memories into a quantum network, and that's also done in QNet. And this is what some of these, what we call temporal metagraphs, look like. Here we've got multiple users with multiple paths and 3 layers of time, quantum memories. And you can see at various points it's switching between layers to avoid congestion, so that they don't have to compete with one another. This is a simple simulation we did with that package. All of these are available, these demos. You can try them out if you like, and see what you come up with. This is simulating a simple network where Alice is on the ground. Then there's another intermediate node, and then Bob is over there, and then there's a satellite moving overhead. And Alice can choose to either communicate via the intermediate node or via the satellite node, or both. So here we've got A to B represents direct, a satellite to B means going via the satellite. That's the curved ones as the satellite is moving overhead. And then you've got the ones where both are purified, and you'll see that For example, this is looking at the dephasing noise of the purified multipaths. You get something that's strictly greater than any of the individual paths. So now we have a way of actually modeling how all of these large-scale networks might actually work with satellites and ground stations and multipath entanglement and everything. Coming back to the earlier discussion on QKD, despite the fact that I said it was stupid and we shouldn't do it, I did it anyway because it's the only thing I can do, which is what I said we could do. So on one axis here, we've got the efficiency of the channels in the network, and on the other axis, we've got the fidelity of channels in the network. And this heat map shows all of the different possible user pairs in the network. And what the trade-off between the efficiency and fidelity is. And these contour lines, they show what the effective QKD bit rate is based on that fidelity efficiency trade-off. So we can get a proper understanding of what the benchmarking performance of the network is for any sort of arbitrary network using this package. All right, so that was QNet. Now let me come back to what all of this actually implies. Imagine we've got the ability to build a future quantum internet with long-range entanglement distribution and everything. And we've also got a future with lots of big data centers that have large-scale quantum computers in them. Let's think a bit more quantitatively about what the benefits are of unifying it all together. So I'm going to introduce this thing here, which I call the computational scaling function, which just says for the number of qubits that I have in my computer, my quantum computer, whether it's distributed or not, this function S tells us for the given application we're using what the classical equivalent computational power of it is. So if you're using a quantum algorithm that has exponentially more power than classical computers, then this is going to be some sort of exponential function. But it varies depending upon the algorithm. Okay, so now suppose that we unify all of the world's quantum computers together. The question is, how much more do we get if you and I both have quantum computers? How much more do we get if we unify them and then you use it half the time and I use it for half the time? In other words, using like a time sharing approach versus me using mine all of the time and you using yours all of the time. Okay, so what we do is we make use of the scaling function, and we say this is the joint power of the entire network, where here I've put in all of the qubits in the entire network. Everybody gets to time share it as a proportion of how much they contribute to the network. And then that gives you what your equivalent percentage of the time shared joint power is. And the question is the leverage, the additional gain you get from doing that is by comparing the ratio of doing it with time sharing or without time sharing. And for classical computing, this leverage function is strictly around about 1, forgetting about whatever inefficiencies may exist. So for classical computing, it makes no difference if I have a desktop computer and you have a desktop computer. If I use mine all the time and you use yours all the time, we both get the same number of CPU cycles as networking them together, and I use it half the time and you use it half the time. For quantum computing, that's not the case. This leverage is strictly greater than 1 and can be exponentially large. In other words, things come for free if we're able to network quantum computers. And the value of that is what really incentivizes the long-term drive to build this infrastructure. It's this relationship, the fact that this is an exponential relationship, which is what is going to be the driving force when we have large-scale quantum computers. That's the economic motive for building the entanglement links between those computers, because as soon as those links exist, all of a sudden they have something way, way more powerful than what they began with without building any more actual quantum computing devices. That introduces all sorts of strategic problems in the world. You can imagine this. This is really where it gets really awkward with doing Zoom conference calls, because when I try to make jokes, I don't know whether people are going to be laughing or sitting there with a straight face thinking, what the hell is he talking about? Is he crazy? So I just have to amuse myself. Anyway, So you could imagine this kind of situation. A Russian bedroom hacker with no direct access to quantum technology delegates a factorizing algorithm to the cloud using homomorphic encryption. Okay, so he's getting some leverage by outsourcing it. It's executed in the United States, despite the fact that it's a Russian bedroom hacker. The Russian hacker uses the number factorization algorithm to crack Hillary Clinton's emails who's using stupid RSA encryption. So the Russian hacker can undermine American security. But the NSA and the FBI have no idea who was behind it because he also has homomorphic encryption, and therefore nobody knows what they're doing with it. They can't tell. And then that is exactly what could lead to this very bold and grandiose vision of everything being unified, not actually turning out that way, because it could actually empower adversaries in ways that they don't want us to have or we don't want them to have, resulting in things splitting across geopolitical boundaries. So this vision for the future may be strategically naive, but if we could just convince ourselves to cooperate, we could all get a hell of a lot more computational power out of it. Anyway, that led me to make some jokes. The fake news thinks the Russians are using our quantum internet, the best quantum internet, against us. I would never allow this ad. I tried to put this in as a figure in the book. And then the editor wrote, Peter, we're going to get sued by Rudy Giuliani. Can you please change this figure? And I said, well, yeah, I agree that getting calls from Rudy Giuliani is generally unwelcome these days. I made a new one for you. And I gave them this one. And then that was going fine, but then on the day of the Capitol riots, they said, Peter, could we just remove the Trump tweet altogether? I said, yeah, you're probably right. So these figures, unfortunately, don't appear in the book. They were in the early draft, which I'll be making available at a later point, but I'm afraid you miss out on these. This is the only place you get to see them. But looking forward, coming back to the very, very first slide of the Chinese satellite network, is that the way forward? On its own, probably not. It has a very, very low bit rate. We've got about 40 decibels of atmospheric loss for every photonic qubit traveling through the air. So for a bell pair where you have to get two of them to different ground stations, that's 80 decibels of atmospheric loss. And what that means is that 1 in every 100 million attempted transmissions of a bell pair is actually going to successfully get to its destination, and that is a very, very low bandwidth. If you imagine you've got a source that has a gigahertz bell pair production rate, now we're getting like 10 per second. That's basically what they measured. So that, it's not an economically viable way to do it using just satellites. You might imagine doing satellites for backbones around the world, where it doesn't have to go through the atmosphere, and have a few ground points where then it spreads out using local fiber networks, for example. And so what we're going to see in the future is some hybrid, I think, of what the Chinese have done. They've demonstrated the ground-based networks. They've demonstrated some elementary satellite-based networks. The satellite ones are very expensive with low bandwidth, but they let you get very long range. The ground-based ones have other issues. You need trusted nodes because we don't have repeaters. At the moment, as you can see from the way I'm putting all of this together, it's all very ad hoc. Lots of independent bits and pieces that aren't properly all fully fitting together yet. And we don't know how that is going to fully look. But this is sort of my vision for how it will look in the future, that we will have this hybrid architecture of sneaker nets and fibers and satellites with all of these distributed quantum computers that are all networked together into a globally unified quantum computer that people can securely access using homomorphic encryption. But then, of course, all it takes is a world war and the whole thing splits in half because America doesn't want China to have access to the quantum computing or vice versa, or whatever the case may be. Regardless, these are the sorts of things that are being discussed in the book, which is now available. And I'm not the only author, I'm the lead author. Rohde Ramakrishnan from IEEE-IISc is also inside this, but it's available now. So that is all of that, and I thought I'd switch over to maybe some questions now.
Thank you, Professor, for this wonderful lecture. It was really good. I'd like to invite the audience right now for any questions and queries they might have. You can either ask them in the chat box or you can unmute yourself and ask.
Yeah, I can see the chat box now. So
Hi, Professor. I have a question.
hi, Bianchi.
So, you said that at one point in the beginning of the talk, you said that when we are trying to transfer the bell pairs, so there could be some. You talked about fidelity of those states. So you measure parity, and when both the states are flipped, then there is you can if there is no distinction because parity wise, but the fidelity is reduced. So I'm just saying कि, if both the states are like both the quantum particles are they are flipped, but what we are interested in is the quantum entanglement between them. So how does that matter if both are flipped or not? How does that
Oh,
reduce the fidelity of that state?
yeah. So if I understand the question correctly, basically saying is that if they both get flipped, which is the ones that we don't want, um, that's still a maximally entangled state. It's just a different bell pair. That's true. The trouble is that the device is unable to distinguish which of those cases it is. So it could be, so it ends up being a mixture of two different bell states. And so if you take a mixture of a bell state and a different bell state, it reduces the entanglement because it's a mixed state. So that's the reason. So the answer is yes, it is still one of two bell states, which are maximally entangled states, but we don't know which one it is, and so we perceive a mixed state.
Okay, thanks.
Uh, I have a question. So you talked about homomorphic encryption and how quantum can allow that. I was wondering, like, for the algorithm which you provided, the receiver or the person who has the task also should have a quantum system to perform these corrective gates in the end, right? Is there a way
Yeah.
to like do it? Is there a way to like send classical instructions which are by default some way encrypted and like, is there a way to do homomorphic quantum encryption of sorts without the receiver having any quantum device?
Oh, um, so are you asking, can you do homomorphic encryption without the client having any quantum resources?
Oh, yes.
Yeah. The short answer is no. So we do have. So let me first explain the difference. Homomorphic encryption is where you outsource encrypted data onto a known algorithm or any algorithm the server is doing, and they send it back to you in encrypted form. And then the slight variant of that is blind computing, where you outsource both the data and the algorithm, and the server is expected to implement the algorithm without knowing what it is because it's encrypted too on the encrypted data, and you get it back. So that blind quantum computing is much more powerful. Classically, blind computing is not possible. It's proven that it can't exist. Classically, homomorphic encryption is possible. However, there are some restrictions. If you're going to do it to universal classical quantum computing, which is the stuff we're really interested in, then there's a very, very significant overhead. It's a large polynomial overhead. So it's still efficient, but the overhead makes it so big that it's not worthwhile outsourcing it anymore. You'd be better off just doing it yourself because of the overhead. So you could outsource the classical information using that kind of technique, but it doesn't have perfect security. To get real perfect security, you really need the quantum mixing effect. So in terms of whether there's a hybrid approach whereby you could send encrypted classical data onto a quantum computer, I don't exactly know the answer to that, but I suspect it'd end up being in the same category as where classical homomorphic encryption is somehow interfacing with a quantum device. But I don't know how well that studied that is.
Okay. Yeah. Thank you. There seems to be two general questions in the chat box. Mrs. Nalini asked, what are the future trends in quantum internet and where do you see it going?
Yeah, the trends are hard to know. Obviously, what the you know the China isn't the only country that has put up a quantum satellite. Lots of countries are attempting to do similar things. The long-term vision would be to have a constellation network of satellites that allow point-to-point communication anywhere on Earth, the way that we're able to do with classical satellites at the moment. Um, you might think that that is, a relatively minor step compared to putting up one satellite. If we can put up one, why not just put up 1,000 more identical ones now that we know how to build it? The trouble is that for them to act as a constellation, they would have to have this quantum repeater type of infrastructure on them. At the current satellite, it's just passive. All it does is sends out bell pairs. It's got a spontaneous parametric down conversion source on it, and it's just spitting out billions of bell pairs all the time. That's all it does, completely passive. If they were to make a link, they would have to be communicating with one another, have quantum memories so that they can hold one another's bits and pieces of information, which we can't even do on the ground properly yet alone in space where everything's moving at massive speeds. I mean, you can imagine that keeping things optically stable for interferometric purposes, when you've got satellites moving at, thousands of kilometers an hour, tens of thousands of kilometers an hour, it's not trivial. So it's not just a simple extension of building more of what we had. It's a completely different generation of technology. Just to even add one more that connects to to another one. So this is very, very long-term stuff when it comes to space. When it comes to the ground, the immediate term, it looks like it'll be more of like the sort of thing that I showed in China, whereby you have trusted node networks around the place. But trusted node networks are only really useful for QKD. They don't actually create long-range entanglement. They're really only useful for creating secret keys, assuming that you can trust the nodes. So the next step has to be making repeater networks that allow things to scale up in terms of length. That's the next thing that needs to be addressed. Lots of people are working on it, but extremely technologically difficult, primarily because of the requirement for quantum memories, where you can hold things for a long time while you wait for other things to come in. So it's a very, very long-term roadmap. And in other words, it's difficult to say anything about trends because we are so early in the development stage of this technology that it's probably premature to even know what the trend is.
Okay. I think the next question is similar to what you had answered. Mr. Jaikumar asks, how much time will the quantum internet take to become like a normal internet?
Yeah, a very long time. And the answer is it probably will never be like the normal quantum internet because it's all about what the demand is for who the consumers are. And primarily, the demand for the classical internet is mobile phones. You don't have any demand for quantum devices on your phones. So like it'd be a much smaller infrastructure by definition, much more targeted to where it needs to be.
Another question, are researchers trying to build quantum repeaters, and where do one start for thinking? Where do one start with this?
Sorry, can you repeat that?
When you want to build quantum repeaters, from where do you start, and how do you do it?
So there's lots of literature on this. I mean, really, the first generation repeaters, it comes down to two things: swapping and purification. People have done both of these experiments. People have done entanglement swapping. People have done entanglement purification. If you want to combine, imagine we want to do to swap two bell pairs and another two bell pairs, and then purify the end. Okay. In the absence of having quantum memory, you need all of those things to succeed at once. And we can't really do sort of push button quantum memories at the moment. We can't do that. So we always seem to run into this problem of having exponential overheads associated with things because we require things to work simultaneously because we can't hold things in memory. Once that technological milestone is addressed and people can make push-button quantum memories where a photon comes in, you push a button, it comes back out, while preserving its qubit structure, that will then pave the way for allowing more things to take place because they don't all have to happen at once.
Okay. Yeah, and also to add to this, I think the next lecture will be about this, so you can tune in for that.
Oh, great.
So I guess that's it with the questions. Any other questions? We can wait for another 1 minute. So I guess there's no other questions. So I'd like to take this opportunity to thank Professor Peter Rohde for the wonderful lecture today.
Okay, so thank you very much, Praveen, for organizing it.
Yeah.
Thank you, everyone.
It was my pleasure, sir. Yeah. So I'd like to thank everyone for attending today, and I think this concludes this lecture. So we will meet you again at 2 o'clock, where we'll have Professor Anil Prabhakar to talk about quantum networks again and its implementations. So I should stop recording now, and I should conclude the meeting right now. You can leave now.